Hi everyone, this is K. Karthik from Triple E department. Now I'm going to explain about graph structures learning from unlabeled data for early outbreak detection. Introduction for graph structures. Graph structure learnings (GSL) is a method of learning the underlying relationships between entities in a network. In the context of disease outbreak detection, GSL can label interactions between individuals or locations to detect abnormal patterns indicating an outbreak. Motivation for early outbreak detection. Early detection of a disease outbreaks is critical for preventing widespread transmissions. Traditional methods rely on labeled data, but in real-world scenarios, outbreaks emerge from unlabeled, unknown patterns. Graph-based methods provide a way to infer patterns from complex interactions. Importance of unlabeled data. In many real-world settings, data labels are not available. Unlabeled data reflects unsupervised learning, where patterns must be discovered without prior knowledge of their structure. Graphs are a natural way to represent relational data, making GSL suitable for outbreak detection. Understanding graph structure learning (GSL) involves discovering the structure of graph, where the nodes represent the entities and the edges represents relationships. The process often involves inferring hidden structures from observed data. In outbreak detection, nodes can represent individuals and edges can represent interactions that facilitate disease spread. How graph structures learning works. GSL algorithms use statistical methods and optimization techniques to infer the most likely graph structures. Features of the nodes and edges, like frequency of interaction, are used to construct the graph. Learning this structure enables identification of key transmission routes during an outbreak. Graph theory overview. Graph theory studies the relationships between entities connected by links. Entities are nothing but nodes and links are nothing but edges. Concepts like degree, centrality, and clustering help in analyzing the spread of diseases in, in a population. Disease transmission can be modeled as dynamic graph, where new edges, interactions form over time. Types of graphs in outbreak detection. Undirected graphs. There are three types of graphs. They are undirected graphs, directed graphs, and dynamic graphs. Undirected graphs represent bidirectional relationships. Examples: collocations of individuals. Directed graphs capture undirectional transmission of disease. Example: for a source to a target. Dynamic graphs account account for time varying interactions, which is crucial for real-time outbreak detection. Learning graphs from unlabeled data. Without labeled data, JSL uses unsupervised learning techniques. Algorithms like clustering and spectral analysis are used to learn relationships. The goal is to identify abnormal structures or anomalies that suggest an outbreak is occurring. Unsupervised learning techniques, clustering, dimensionality reduction, graph embedding. These are three types of unsupervised learning techniques. Clustering groups data points based on similarity. which helps in finding communities and clusters of disease spread. Dimensionality reduction techniques like PSA, principal component analysis, reduce the complexity of the data. Graph embedding maps nodes into low dimensional space, preserving key structural information. Advantages of graph structure learnings detects emerging outbreak early by analyzing complex patterns of transmission, handles the large scale high dimensional data typical in epidemiology, captures dynamic and evolving structures of disease spread, making it adaptive to changes. Challenges in graph structures learning. Scalability, noise are the most challenges in graph structure learning. Scalability. Large data sets with millions of nodes can be computationally expensive. Noise. Real world data often contain noise, which can mislead the learning process. Dynamic nature of graphs requires algorithms to be continuously adaptive. Applications in epidemiology, early detection of disease outbreaks. Example, COVID-19, influenza, contact tracing by identifying key individuals in a transmission chain, monitoring the spread of infections, diseases across geographic locations. Algorithmic approaches to GSL, spec, spectral clustering, graph neural networks, variational graph atom coder, identifying clusters of similar nodes, useful in detecting communities of infection. Graph neural networks (GNN) learns node embedding while preserving graph structures. Variational graphs autoencoders used for unsupervised learning of graph structures. Role of machine learning in outbreak detection. Machine learning algorithm can predict outbreak trajectories by analyzing historical and real-time data. Supervised and unsupervised learning models are applied to classify outbreak phases. Combined with GSL, ML can provide accurate and real-time predictions. Evaluating GSL models. Metrics like precision recall and F1 score assess the accuracy of outbreak detection. Graph metrics like modularity and node centrality measure the importance of nodes in the spread of disease. Across validation and bootstrapping are used for model validation. Tools for graph learnings. Network X Python, a powerful tool for graph creation, manipulation, and analysis. Gephi visualizes large-scale networks to identify outbreak patterns. PyTorch Geometric enables deep learning on graph data, essential, essential for GNN applications. Computational requirements. GSL algorithms can be computationally intensive due to the large-scale nature of epidemiological data. High performance computing and GPU acceleration may be necessary for real-time applications. Cloud-based solutions offer scalability for handling large datasets. Real-time data for outbreak detection. Real-time data, such as mobile device tracking, can be used to construct dynamic graphs of population movements. These graphs can be help identify outbreak hotspots and areas of concern. Integration with IoT devices and social media feeds enhances early warning systems. Graph neural networks for outbreak detection. GNNS can model complex non non-Euclidean data typical in epidemiology. These models learn node embedding that capture both local and global structures. GNN have shown promise in predicting disease transmission paths and outbreak emphasis. Applications beyond outbreak detection. Graph-based learning is not limited to outbreak detection but also finds applications in social network analysis, recommendation systems, and cybersecurity. Anomaly detection in financial transactions and fraud detection in networks. Traffic monitoring and urban planning using dynamic graph models. Integrating GSL with policy decisions. GSL models can provide decision makers with early warning signs, enabling proactive interventions. Policies regarding travel restrictions, quarantine, and vaccination can be fine tuned based on GSL predictions. Real time insights can help allocate medical resources more effectively during an outbreak. Challenges in real world applications. Data scarcity and incomplete information may hinder the accuracy of outbreak predictions. Integrating diverse data sources, social media, medical records, environmental data poses a challenge. Ethical concern about privacy and sec- data security remain paramount. Differences. We keep TN keeps semi-supervised classifications with graph convolutional networks in 2006. J. et al. Graph Neutral Networks, a review of methods and applications in 2020. D. Exiu et al. Early disease detection using graph representation learnings in 2022. Conclusion. Graph structure learnings offers a powerful approach to detecting outbreaks from unable data by modeling the complex interactions between individuals and populations. GSL provides early warnings of potential outbreaks. Continued advancements in machine learning and graph algorithm with enhanced outbreak prediction capabilities. Thank you.